Good morning. I am Ruben Ruiz from University of Cantabria. I am going to talk about how to detect automatic stream using a Brillouin Optical time domain analysis sensor and principal component analysis and artificial neural networks. This presentation is divided in 4 parts. First of all, a brief introduction. After that, I continue with some theoretical aspects about Brillouin sensor, principal component analysis, and artificial neural networks. After, some results and the conclusions. Nowadays, structural health monitoring has converted in a wide working area due to the requirements in terms of safety and security. So we have to develop some sensors to try to avoid or to detect cracks on dams or on bridges. Also detect leakage on pipelines. So we need to develop some sensors, like it could be optical distributed sensors. With this kind of sensor, we can measure temperature, strain, or both at the same time, always depending on the type of sensor. The sensing element can be a single model fiber, and depends on the configuration, we can achieve high spatial resolution or long range measurements, and the number of points of resolved points depends on also the configuration, but it's near 1,000, more than 1,000, and then the last news says that 1 million points of resolved points. This kind of sensors are based on scattering, that it could be linear scattering like Rayleigh, or non-linear scattering, that it could be Brillouin or Raman. The first one is based on acoustic waves and Raman in thermal waves. If we want to develop a sensor using Raman, we have to measure the change in the intensity. But if we want to develop a Brillouin sensor, we have to measure the change in the Brillouin frequency shift in the points of the fiber. So, as we can see in the expression, the Brillouin frequency shift depends on the acoustic velocity, that also depends on temperature and strain. So if we measure this Brillouin frequency shift, we also could measure the temperature or the strain in the fiber. As we can see in the graph, if we increase the temperature into the fiber, also the Brillouin frequency shift increase. There is a linear correspondence between these two magnitudes, and it's the same effect if we apply some strain to the fiber. We can see that if we apply strain, the Brillouin frequency shift is also increasing. And the expression is the next, where CT is the coefficient of temperature, that is 1 megahertz per degree, and the coefficient of strain is 1 megahertz for 20 microstrains. There are different kinds of Brillouin sensors, but here we are going to explain some details about the Brillouin optical time domain sensor, Brillouin optical time domain analysis. Here we use a pulse bound signal and a contrapropagating continuous wave in order to achieve an interaction in the optical fiber. And if we measure this interaction in the time domain, we could achieve to obtain distributed information along the fiber. The pan-proof frequency shift is chosen in a range of frequency near to the Brillouin frequency, that in single model fiber is between 10 or 11 gigahertz, more or less. And here we can see that the correspondence between the frequency and the temperature, and if the change on the frequency is also a change on the profile of temperature profile. But this configuration have some drawbacks, like it could be the limited spatial resolution of 1 meter due to the phonon lifetime, the reduced signal to noise ratio, and also the time that we need to perform the complete analysis. But we try to avoid this last drawback using this other configuration, that is slope-assisted BOTDA, where the pump frequency is fixed at the half of the Brillouin gain spectrum. So if we have some dynamic strain into the fiber, this effect modulates the Brillouin frequency. Then the gain of the process is also modified, because we have in different part of the slope of the Brillouin spectrum. So it's very useful for try to measure dynamic strains or dynamic change in surrounding the optical fiber. But we also want to apply some extra processing to the optical signal. So we try to apply principal component analysis. That this is an orthogonal transformation to convert a set of normally correlated variables into a linearly uncorrelated variables, like we can see in the graph. So there are some data that is correlate, and with after processing, we can get a data dimension, and it's easier to discriminate the different components. But also we want to add some extra artificial intelligence, and we use artificial neural networks. That is a computational model inspired by human brain and the nervous system, and are used to estimate a lot of inputs and try to obtain a known functions. These systems there are systems of interconnected neurons, and they try to emulate the human brain. So they try to learn from data. They have characteristics like pattern recognition. Okay. And now we can observe the results that we have obtained with this technique. The experimental setup is in the graph. We can see the central part of the graph. There is a fiber of 80 meters, where is divided in 4 different regions of 20 meters. The first 3 meters of each region is attached to a static positioner and an automatic strain. It's an automatic spring in order to produce the automatic strain into the fiber. After we obtain all the data, we proceed to apply principal component analysis in order to reduce the data dimension, and after that we use the artificial neural networks, first with the training state and after with the test, in order to process all the inputs and try to obtain the desired output. And here we can see the results. The first 4 graphs are the first 4 principal components of the analysis, and it's we can clearly identify all the 4 zones where we apply the different strains. And in the 5 graph, we can see the situation where we apply the strain, or when we don't apply any strain into the fiber. Now, if we want to process this other data with an artificial neural network, we can achieve this classification. Here we can see the classification rate that is near to 91%, and we can observe from 1 to 4 is identified with the 4 zones of we said before, and the 0 is when we don't apply any strain to the fiber. We prove this with different number of neurons and different kinds of configuration, and the best rate is 91% of accuracy. So the last is the conclusions. Dynamic events have been successfully detected and categorized by means of slope-assisted BOTDA, And we use also PCA and artificial neural networks to help our classification. The first four components of PCA allow clear identification of the four different zones, and the 5 PCA is very related with the situation that we apply some strain or not into the frame. We also get a classification performance of 91%. Thank you so much, and I want to acknowledge that this work has been supported by the FOSFO.